Hello all. In this video we'll be discussing about the transfer function of electrical system. So before getting into that, but just we need to know that the relation between the voltage and current across various electrical elements. So we have totally three passive elements: resistor, inductor and capacitor in an electrical network, for whose the voltage and current relationship are given listed out in the table. The first four columns in the first three columns in this is representing the voltage current and current voltage relationship among the three passive elements. Okay, that is, if you see the column number 2, you have this voltage and the current relationship with respect to a capacitor, resistor and inductor, and the current to voltage relationship for the inductor capacitor in the column number 3, and then the charge to the voltage across these elements in terms of this. And then in the S domain, the impedance value and the admittance values of the respective elements are listed here. For capacitor, it is 1 upon Cs. For impedance and for admittance, it is inverse of the impedance, so it is Cs. For resistor, impedance is R and admittance is 1 by R. And for inductor, the impedance is Ls and the admittance is 1 upon Ls. Okay, and this circuit, which we already discussed during the lab session, I have taken a simple series RLC circuit. So for this circuit, I need to find out the transfer function by considering the output voltage across a capacitor as the output variable, and with my supply voltage to be the input variable. So in order to derive the transfer function of this simple electrical circuit, this is a single loop circuit for which I am writing the Kirchhoff voltage law. So I arrive at this equation: V is equal to R into I of t plus L di by dt plus 1 by C integral I dt. And the output voltage across a capacitor, which is the output variable of this system, is expressed as 1 by C integral I dt. Now I need to find out the value of I in order to get the value of Vc of t. So in order to achieve this, I am going to use a Laplace transform with 0 initial conditions for the equation 1 and the equation 2. So if I take the Laplace transform for the equation 1 and 2, I will get this v of s by s is equal to R into I of s plus SL I of s into plus 1 by SC into I of s, and Vc of s is equal to 1 by SC into I of s. So from equation 3, I will be finding out the value of I of s, and then I will substitute that in equation number 4 in order to get the value of Vc of s. So this is how it is been formulated. So from this is the equation 3. From equation 3, we are getting the value of I of s. Upon substitution in the of equation number 4, that is for Vc of s, and upon simplification, we arrive at the transfer function of the simple electrical circuit of this. The same circuit can be solved easily in an alternate way, and by using the transformed network. So what I need to do is, I need to transform my actual circuit into an S-domain equivalent network by replacing the impedances of the actual circuit into an equivalent S-domain by mapping into this table, from this table. Okay, so from this table, if I want to replace a capacitor C, I should use the value of impedance to be 1 by Cs. If it is for resistor, I should use R. If it is an inductor, I should replace L by S into L. So if I perform this substitution, then I will get the transformed network, and my time domain voltages and currents must be transformed. Again, it should be taken the Laplace transform the S domain as V of s, I of s and Vc of s. Now to this circuit, again I will be writing the V of KVL equation, that is your V of s by s is equal to R into I plus SL into I plus 1 by SC into I. So again, I here in turn it stands for I of s. So from this I can find out what is my I of s, and then I can substitute in this equation. Upon simplification, I will be getting the same equation. So there is a slight difference, or it's an easier way to predict, is an easier way to compute the transfer function of an electrical network. So let us solve one example of similar kind. Okay, I'm considering a two loop network for which I need to find out the transfer function I2 of s divided by V of s. Okay, this was a circuit given to me. First, I need to determine the transformed network. I need to find the transformed network. A transformed network or circuit by replacing inductance should be replaced with SL, and the capacitor should be replaced with 1 by SC, and the R should be replaced by R. V of t should be replaced with V of s, and I of t should be replaced with I of s. So like this I need to have it. So this is one such transformed circuit for which I need to find out, I need to write the loop equation. Okay, so if I try to write the loop equation for the first one, for loop 1, for loop 1, KVL is given by uh, V of s is equal to R1 I1 of s plus SL into I1 minus I2. Okay, and when it comes to the second, for loop 2, we have this. Before that, let me rearrange this by combining the like terms. So let me take it as V of s is equal to R1 plus SL into I1 minus SL I2. Okay, and for loop 2, writing the KVL, so 0 is equal to R2 I2 plus 1 by SC I2 plus SL into I2 minus I1, and in turn again, as like how we did in the previous case, I am going to group in terms of this. So minus SL I1 plus R2 plus SL plus 1 by SC into I2. So this is a let me take this to be equation 1 and equation 2. Now I can write equation 1 and 2 in matrix form. So now I can write this equation in the form of matrix. So where I will be having that V of s and 0 is equal to, and here I have R1 plus SL here, and then here I have minus SL, and again here it is minus SL, and here in this case I have R2 plus SL plus 1 by SC multiplied by I1 I2. And now in my case what I need is, I need to find out I2, so I can apply by Cramer's rule. By Cramer's rule I can write I2 is equal to delta 2 by delta, where this is my delta. Okay, and here delta 2 I can write this as R1 plus SL 0 and here V of S, so here it is minus SL 0 divided by the determinant value. So the determinant value determined by delta, so which is given by SL V of S divided by delta. And once if I try to find out the value of determinant delta, that is R1 plus SL minus SL minus SL R2 plus SL plus 1 by SC. Okay, the determinant value deduces to R1 plus R2 to LC S square plus R1 R2 C plus L into S plus R1. So this is the value of delta. Upon substitution, we'll get the value of I2. So what is our expression actually? My transfer function is G of S is equal to I2 of S divided by V of S. So this is equal to SL divided by delta. Okay, so I have this here. This is my I2 of S. I2 of S divided by V of S is nothing but SL divided by delta, and the delta value is this one. So like this, we got the transfer function of the electrical circuit by using the transformed domain. Okay, and let us consider the another example of an operational amplifier. So where I need to find out the ratio of V0 of S by Vi of S. Okay, and the op-amp has a characteristic of gain. An ideal op-amp, the gain A is the ratio of output voltage to the input voltage, is infinite for an ideal case. For practical case, it is of very higher value, which means my Vi is nothing but the voltage available at this point. The differential voltage is nearly equal to 0, which indicates my Vi is nearly equal to 0, and therefore my A is equal to infinite. Okay, so one such amplifier is shown over here. So for which I need to derive the transfer function. Okay, so in this circuit, this is the non-inverting terminal, this is the inverting terminal of the operational amplifier. The potential difference across these two terminals is nearly equal to 0. Why? Because since the positive non-inverting input is connected to the ground, here the potential is 0 volt. By the concept of this virtual ground, that is the ideal infinite gain, this voltage difference is 0. Since this is 0, I am assuming the potential at this node is also equal to 0. So let me designate this to be node A. So at node A, if I applying KCL, we have, see, I1 of S is flowing from the input to the node A. I2 is flowing between output voltage to the node A, and IA is nothing but the current entering into the operational amplifier. Okay, so at node A, if we take it, I1 plus I2 is equal to IA, and if you take the input impedance of an op-amp, the input impedance of op-amp is infinite, and hence since the input impedance is infinite, the current drawn by the op amp is 0, and therefore we have I1 is equal to minus I2. Now I need to find out what is I1 and I2. So I1 is Vi of S minus the voltage at node A, V1 of S, divided by the impedance Z1. And similarly I have that for I2 is, it is flowing from V0 to V1, V0 of S minus V1 of S divided by Z2 of S. Now V1, since V1 is equal to 0, that is the concept of virtual ground, we have Vi of S is divided by Z1 is equal to V0 of S divided by, here it is, I should accompany the minus sign, minus V0 by Z2 of S. And now the gain, amplifier gain, AV is V0 of S divided by Vi of S. So from this we can write V0 of S by Vi of S is equal to minus Z2 of S divided by Z1 of S. So this is the transfer function of this operational amplifier. Okay, so it's quite simple. If there is any combination of impedance, see, it cannot be purely resistance, it can be a combination of resistor and capacitor, a resistor, inductor, capacitor connected in series or parallel. By using this relation we can find out the transfer function of the amplifier. So let us deal with a small example where we have Z2 is R2 connected in series with a capacitor, and Z1 is your R1 in parallel with an capacitor, in parallel with the capacitor. Okay, so now in this case, since we need to use this simplification here, a series parallel combination of this one. So what I can write here, this to be equal to S R2C2 plus 1 divided by SC2, and here it is R1 R2 divided by R1 plus R2. So in that case I have Z1 divided by SC1 divided by R1C1S plus 1, the whole term divided by SC1. So in such case this SC1 and SC1 will get cancelled. So my Z1 value is R1 divided by R1C1S plus 1. And what is my transfer function? The transfer function, that is A is equal to V0 of S by Vi of S is equal to Z2 of S by Z1 of S. Since it's an inverting amplifier configuration, I will have a negative sign over here. So the value of Z2 is SR2C2 plus 1 divided by SC2 divided by, and Z1 value is R1 upon R1C1S plus 1. Okay, now we need to substitute the values of R1C1, R2C2 in this expression to get the value of the transfer function V0 of S by Vi of S. Okay, so if you take it here, I, okay, so let me substitute this. Yes, R2 value is 220 kilo ohm, so I am taking it as 220 into 10 power 3 into C2 value is 0.1 microfarad, so 0.2 into 10 power minus 6 plus 1 divided by S into C2. So S into C2 is S into 0.1 into 10 power minus 6 divided by R1. R1 is 360 kilo ohm. 360 into 10 power 3 divided by R1 C1 S plus, so I have this 360 into 10 to the power of 3 into 5.6 into 10 power minus 6 into S plus 1. So I need to simplify all these things, and again I should not forget the minus sign over here in all the cases. It is important. So at last I have this as, upon simplification, it is minus 1.232, and in the fraction I have this s square plus 45.95s 45.95s plus 22.55 divided by s. So this is V naught by Vi of s, the required transfer function of the amplifier.